Some people like matrices because it's just simple adding, subtracting, and multiplying are the only operations that we are going to be dealing with. I don't know. I personally wouldn't like just using elimination. But when you get to 3x3 systems, sometimes it's a little bit easier to deal with using your matrices. Okay, I am going to show you how your calculator will do it for you nice and quickly, so you can use that to check your answers, but you do need to show all your work. There's no way just to say, oh, I got the answer by getting it with your calculator, because you have to show all of your steps for this. Okay? Everybody good to go? Ready? All right, so what is a matrix? Well, brighten up your day. Yeah.
I'm trying to make this up.
So a matrix is an ordered array of numbers. Yeah, array of sun.
Yeah, it's supposed to be funny. Sun, array.
Okay, so here's an example of a matrix. So we have in this matrix 3 rows and 3 columns.
Hopefully you can teach us this better than Miss Wilson.
Miss Wilson loves her matrices.
Oh, yes.
Now, to name a matrix, to tell its dimensions, I guess really is what we should be doing. Sometimes they'll put like, oh, that's not what I want to be doing. That's like a highlighter. Sometimes they'll put A is equal to, so then we could call it matrix A. But when you go to name the dimensions of a matrix, it's row by column. In this case, it doesn't really matter since the row and the columns have the same amount of digits. But this would be a 3 by 3 matrix. Okay, so you go row by column. So what would a 2 by 3 matrix look like? So a 2 by 3 would have 2 rows, 3 columns. So maybe something like that. So 2 rows, 3 columns would be a 2 by 3. What would a 7 by 1? 7 by 1 would be 7 rows, 1, 2, 3, 4, 5, 6, 7, 1 column.
Nice.
Right? Okay, so given a matrix, we should be able to decide what the dimensions are. You go by row by column. Okay? So far, so good.
Yes.
Okay. All right. We already did that. So let's just go through these really quickly. You don't even write these in your notes. What would be the dimensions of A? 3 by 3. Dimensions of B? 1 by 3. And C would be 4 by 1. Good. All right. So another thing that we have vocabulary-wise is something that's called the element of the matrix, or the matrix element. When we have a matrix element, the element is each number in the matrix.
What's your favorite kind of matrix?
Probably a
1 by 1.
1 by 1. 2 by 3. Probably the best one for your row operations. All right, so each element is called, number is called an element. So if I gave you matrix A here, it's a 3 by 3, 3 rows, 3 columns. We've got 17, 24, 3, 10.4, 12, 15, 9, 30, and 15. If I wanted to identify element A sub 1, 3, so A subscript 1, 3. I'm not going to say 13 because it's not 13.
No, will the answer be 3?
Would the answer be 3? Yes. So what this means is I'm going to look in row 1, column 3. So if I go to row 1, well, 17 would be column 1. In row 1, 24 would be column 2. So in row 1, column 3 would be element 3. What would be a 2-1? 10.4. What would be a 3-3? 15. Good. Okay. So we can identify elements. We can identify dimensions. So far, so good?
C.
Okay. All right. So now we're going to get to our favorite type of matrices, which is something that's called a square matrix. And a square matrix is a matrix that has the same number of rows as columns. So a 2 by 2, a 3 by 3, a 4 by 4,
25 by 20.
25 by 25. That would be insane.
I'm 100 by 100.
Even more insane. Okay, so square matrices are when you have something like a 2 by 2, a 3 by 3, a 4 by 4. Hopefully we won't ever have to go above a 4 by 4. 5 by 5, anything like that. All right, so we got matrices, we can tell dimensions, we can identify elements in a matrix. We now know what a square matrix looks like. So now we're going to turn that square matrix, and we're going to turn it into what's called an augmented matrix. So an augmented matrix has a vertical bar that separates the columns of the matrix into 2 groups. So for example, if I made a 2 by 2 over here of, let's say, 1, 2, 3, 4, and then I put a bar and put 5, 6 over here, that would be an augmented matrix. I have the vertical bar that's separating your columns into 2 groups. It just so happens that my group over here is a 2 by 2, my group over here is a 2 by 1.
Why would you do that?
Because when we get to solving systems, if you can envision this, these would be your coefficients of your x and y, and these would be your constants on the other side of the equal sign. So your equal sign is going to become that bar in an augmented matrix. Okay? If it was a 3 by 3, you'd have 3 by 3 on the left, and then you have your 3 solutions on the right. All right, so augmented matrix. Oh, already did an example there. See, same thing. Got it? Good. All right, so now here comes the fun. You want to get this stuff written down. These are the rules that you can follow when doing matrix row operations. And we're going to use matrix row operations to solve systems of linear equations. And these are the operations that you are only allowed to use. Can't do anything but these. So rule number 1. Any,
Follow these rules in order.
you do not need to follow them in order, no. Thank you for asking that. Any 2 rows of the matrix can be interchanged.
All right.
So I can take row 2 and I can move it to row 1 and bump row 1 to row 2. So I can interchange any of my rows. I cannot interchange any of my columns. Rows can be interchanged. That's row 1 or rule 1.
Question.
Yes.
But what about when you have, like, when you're doing this subscript thing? Isn't that going to be changed? Like,
So then now I change where your element's location. Yes. But that's okay. Rule 2. Rule 2. The elements of any row may be multiplied by any non-zero number. So I can multiply a whole entire row by a number, as long as it's not 0. It can be any number that I possibly want. Sometimes it will be a fraction, sometimes it will be a positive number, sometimes it will be a negative number. Rule number 3. And this is the most important one. Any row may be changed by adding to the elements of the row the product of a real number and the corresponding elements of another row. So we can interchange any row, we can multiply any row by a number, and then we can add the elements of a row to the product of a real number and the corresponding elements of another row. All right, let's see what this looks like in action. Are we ready?
Ready.
Okay. Ignore all this. Okay, here's our problem. We're going to use row operations to solve the system. Now this looks familiar to us. X minus 3y equals 1. 2x plus y equals negative 5. If this was on your quiz today, you would do probably the elimination method and probably eliminate what? The x's, solve for your x, for your y's first, then get your x's. You would do substitution, that would work also. But we're going to learn a new method using matrices and row operations. So I'm going to turn my system into an augmented matrix. Here we go. To create it, all I'm going to do is focus on the coefficients. The coefficient of this x is what number? 1. Coefficient here is negative 3. I'm going to put my bar where my equal signs are. Then I have a 1. So there's my first row. Row 2. 2, 1, negative 5. Now my ultimate goal is to get 1s on my diagonal. Wow, look, they're already there.
Nice.
And I'm trying to get 0s every place else, which I don't have 0s every place else. Okay, so the trick is to start with the lower left-hand corner and try to turn that into a 0 first. Or, if you want to think about it elimination-wise, how can I eliminate the x's? What do I need to multiply this by to eliminate negative 2? So what do I need to multiply row 1 by to turn this into a 0? Negative 2. Now watch. This is how you show your row operations in nice organized fashion. You have to show everything you're doing. So what are we doing? We're taking negative 2. We're multiplying it by row 1. And then we're going to add that to row 2. So this is going to be a string of steps. So when I do that, that's going to create a new augmented matrix. Now what I like to do is I actually physically like to show the actual multiplication. I'll do it in a different color. So I like to put a little times -2 times -2 times -2 to remind me that's what I'm doing. So if I do that, so what are we doing? We're multiplying -2 times every element in row 1, and then we're going to add it to row 2. So -2 times 1 is -2 plus 2 is 0. So now this element just turned into a 0. Now let's do the second column. -2 times -3 is 6 plus 1 is 7. Oh boy, that got rid of our 1. That's okay. We can get that back easily. Now let's do with the third column. -2 times 1 is -2 plus -5, -7. All right, so that was our third rule for what we can do for operations. Because I took this and added it to this, my row 1 does not change. The only one that changes elements is whatever your second row is listed here. Okay, so there was one operation that we did. No, we lost our 1s on our diagonals, and this is not a 0. So now let's think about this. Would it be easier to turn this into a 0 or turn this into a 1 right now?
How would you both do this?
Turn 7 to a 1.
Yeah, because what would I have to multiply -3 by to make it become a 0, or with a 7? Yeah, it's going to be a crazy fraction, right? So let's turn this into a 1 first. Well, what do I do to 7 to turn it into a 1? Divide it by 7, but we can't divide by something. We can only multiply by 1/7. So I'm going to take 1/7 of R2. That's going to be my next move. So I'm not touching R1 again, so R1 has not changed in our 2 steps that we've completed so far. R2, row 2, becomes 0, 1, 1. It's a little bit nicer looking. So now, how can I turn this into, turn this into a 0?
-1 on the bottom.
Multiply row 2 by what? If this becomes a +3, then when I add it, won't that go to 0?
Yeah.
So, next step, I'm going to take 3 times R2, and I'm going to add it to R1. So, R2's not changing, so rewrite R2. Now what's our new R1 going to be? Well, it helps me to actually show the math that's happening, so I'm going to do it in purple here. What do we say? We're going to multiply this by 3, multiply this by 3, multiply this by 3, and then add it. So, 3 times 0 is 0. 0 plus 1, that's going to stay a 1. 3 times 1 is 3 plus -3, now makes that become a 0. And then 3 times 1 is 3 plus 1 is 4.
It's supposed to be a -1 on the end, not a positive.
Where? Oh, -1, thank you. See? And there's tiny mistakes. So then it'd be -3 plus, so yeah, it's -2. Okay, so do we have 1s on our diagonal? Do we have 0s every place else? Now watch the magic. This represented the coefficients of which variable? This represented the coefficients of which variable? So 1y is equal to 1x is equal to -2. So I get x to equal -2, y to equal 1. Thank you. -1. So make it fancy.
Can we just do elimination?
Nope, the rest of this whole chapter is matrices. So let's check it. -2 plus 3, is that 1? Yes. 2 times -2 is -4. -4 minus 1 is -5. Done and done.
I don't like this. Too much work.
It is a lot of work.
Just to get that.
All that just to get -2 and -1.
All that to get -2 and -1.
Where if you did the other method, actually any of the other methods would have been a lot faster.
Right, but when we get to the 3x3s, sometimes it gets a little bit easier to do matrices. All right, do we want to try another one, or you think you got it?